Welcome back. Some of the problems that you will encounter in the plane involve constant acceleration. That's constant vector acceleration, because remember, if we're dealing with motion in the plane, we have to worry about the x and y components of acceleration. And we've already seen that for constant acceleration, the position along the x-axis at any time can be expressed in terms of the initial x-coordinate, the initial x component of velocity, and the acceleration along that axis. We have a similar equation for the y-coordinate. If we're doing a problem in projectile motion, or free fall, as I like to call it in 2D, then very often the y acceleration would be written as negative 9.8 or positive 9.8 if you put the positive y-axis pointing downwards. But it doesn't have to be gravitational acceleration. The only requirement is that the acceleration is constant. Now, I tellingly left some space here between these quantities because notice how x naught is lined up with y naught, v naught x is lined up with v naught y, and a sub x is lined up with a sub y. They fall into columns. So what we can do is enclose those corresponding quantities in columns, or in parentheses, I should say, and recognize that these are actually the x and y components of a special vector. What would you call the vector whose components are x-coordinate and y-coordinate? Well, those components specify your position. So clearly, this is the position vector r. This is the position vector at time 0. This is the velocity vector at time 0. And lastly, this would be the acceleration vector during the relevant time interval. And that means that we can succinctly write these two equations as a vector equation. You see that? Think of this r with the arrow over it as a column vector with components x-coordinate and y-coordinate. Similarly for the position vector at time 0. So this is a compact way of writing, for our purposes, two equations simultaneously. And what's nice about it is that there's really nothing new to memorize. It's still the 1/2 at squared equation. You still have your v naught t, your 1/2 at squared, your initial position, but instead of dealing with quantities x or y without the arrow, we will refer to the position as r, and it's a vector. That's why it's got the vector symbol. Okay, now if you were doing a problem with constant acceleration and your particle's moving around in 3 dimensions, it's got freedom to move along the x, y, and z axes, then you could use this equation as a compact way of writing 3 equations simultaneously, where the third would be z equals z naught plus v naught c, etc. I don't think we will ever do that in this class. We stick to 2-dimensional problems in a plane. So why don't we look at one of your homework problems that makes use of this equation in particular. This is number 44 from chapter 444. It's another one of those problems that must have been written prior to the year 2000 because they have to make up a planet name. Planet Zeta, we don't need made-up planet names anymore because we already know about thousands of planets outside our solar system. Okay, in any case, we're told that at some particular time, this spaceship is at, oh, you know, I guess I lied, didn't I? Just a moment ago I said we're only going to do 2-dimensional problems, and here in your homework you have a problem that takes place in 3 dimensions. That's fine. It's easy to generalize from 2 dimensions. We'll just use the same equation. Okay, so they're not calling it r sub 0, r naught, but we can infer that that's really the appropriate label because they give us the position of the spaceship at some particular time. Let's just call that t0 equals 0 seconds. So this would be r naught. And they're specifying the position in units of kilometers. Not only that, but it says 10 to the third. So this is really 600,000 kilometers along the x-axis. And they pick these ridiculously large numbers because, you know, if you're out in space in a spaceship, presumably you're covering very large distances. So let's agree right now that when I work the problem on paper, I will be measuring distance in meters, and I'll do time in seconds. Those are not SI units, so yeah, we'll deal with kilometers per second and kilometers per second for velocity and acceleration, respectively. You can use any units you want, whatever's convenient, as long as you indicate that in your work. Okay, and they tell us that the velocity at that time is this many meters per second. Well, that's in meters per second. I'll have to convert that into kilometers per second. And again, they didn't call it v naught. I will add the sub-zero label because we're recognizing that's the velocity at some initial time. It's the same time at which the position takes on this value. Okay, they give us the acceleration also in meters per second squared. I'll have to put that in kilometers per second squared if I want. And they give us the time interval. So what do you notice about this acceleration? There's no t's in there. It does not depend on time. The x component is just a number. The k component, which is the z component, is also just a number. So we know the acceleration is constant. We can go straight to our constant acceleration kinematic equation in vector form. They would like to know the spaceship's position when the engine shuts off. So if you read it, it just means at the end of that 35 minutes of constant acceleration. In other words, we will use the equation for position as a function of time. Give the answers, or give your answers a position vector measured in kilometers. That's why I will choose to stick with kilometers for distance, so that our output is in the units asked for by the problem. Here I've written out in column form the three relevant vectors. We need the initial position vector, the initial velocity vector, and the acceleration vector. Again, note this is a constant. As far as the units, they gave us these numbers already in kilometers, so there's no need to convert. This is 600,000 kilometers. However, the velocity was given in meters per second. I think they said the x component of velocity was 9,500 meters per second. Well, I can multiply by 1 kilometer for every 1,000 meter, or just recognize that I would have to move the decimal place 3 to the left, and that's where I got this 9.5 kilometers per second. And I dropped a couple of the zeros when I wrote it out, the trailing zeros. So the velocity is in kilometers per second. That's not the SI unit. And I wrote my acceleration as 40 thousandths of a kilometer per second because they gave the x acceleration as, what was it, 40 meters per second. And just like before, you can easily convert that into kilometers per second. So you could write it like that, or use scientific notation, which I chose to do here. So now that I've got my three column vectors, I can use the equation presented in PowerPoint, the position at any time. I kind of like to write it out in column vector form and then just go across each axis at a time and evaluate. So we've got 600, and this time I'll suppress the units so that I don't clutter the page. This is my R naught plus, remember now it's initial position plus V naught t. So I have to take my column vector of velocities and multiply by t. And then it's plus 1/2 at squared. So 1/2 times the column vector for A, that's 40, 0, negative 20. Don't forget the power of 10 to the negative third times t squared. This will allow me to calculate the position vector at any time. I would just plug in the time here and here, evaluate the x-axis, evaluate the y-axis, same for the z-axis, and then I have my final column vector that specifies the position at any time. And I believe they were asking for the position at t equals 35 minutes. Okay, well remember, all of these quantities are expressed in kilometers and seconds. So if I've got the acceleration in kilometers per second, I really need to plug in my time in seconds. So let's evaluate at t equals 35 minutes. And of course, there are 60 seconds for every minute. So we're actually plugging in what number in seconds? 35 times 60, 2100 seconds. Now you could, it's kind of fun, is it? Maybe a little bit. To try to visualize this spaceship out in space with your x, y, and z axes and picture where the spaceship is. It's a little to the right, it's a little backwards, and it's a little up. Kind of picture where it is in space, which direction it's headed. It's going in the x direction, and which direction it's accelerating, which is it's got an acceleration this way and into the page, and try to picture where it would wind up after 35 minutes. Just ballpark. There's no need to do that. You don't actually have to imagine things. Most of what you do in this class, doesn't require imagination. It's nice when you can bring that to the table, but a lot of it's very procedural, which is good for you, right? Because that's good for problem solving. Let's plug in the time now. So the position at 2100 seconds equals, okay. I guess I could evaluate these each individually, or should I do it all at once? Yeah, why don't we do this? I'll put one big column vector now that's 600 times 10 to the third plus, okay, well 9.5 times t is 9.5 times 2100. So the contribution from this middle term is 19,950 plus, and then I'll evaluate, I'm going across the top row here, so it's 1/2 times 40 times 10 to the negative third times 2100 squared, and I get this number, 88,200. So I would then have to add all those up. Now I'm ready to do the y component, which is the middle row, 400 with the minus sign. I'll just write it like this. Plus, there's no contribution here, 0, that's easy. And same here, the middle component is 0 there. Okay. Now we've got 200 times 10 to the third plus also 0, that one's easy. And then lastly, 1/2 times 20 with the minus sign and times 10 to the negative third, don't forget that, times 2100 squared equals negative 44,100. And I feel like, no, I was going to say I thought I multiplied this incorrectly, but I don't think I did. Let me check this top number. I'm going to make sure I squared 2100. 0.5 times 40 times 10 to the negative third times 2100 squared. Okay, I did that right. So lastly, I could just add all these up, and I would get my various coordinates, position coordinates, at time 35 minutes. In which units? Well, since I plugged everything in kilometers and seconds, then my units will come out in kilometers. So what do we have? 600,000 plus 19,950 plus 88,200. Here's the final x coordinate, 708,150. Let me check the solutions manual. What a relief. They rounded. My answer's better. Negative 400 times 10 to the third. Okay. I'll just write that with all its digits. Negative 400,000. Same answer as the book. And lastly, 200,000, whoops, 200,000 minus 44,100. And I get, now why do I not have a minus sign here? The book has a different answer. Did I do this correctly? 1/2 times 20 with the minus sign times 10 to the negative third times 2100 squared minus 44,100. This number is bigger than that, so it should come out positive. I think your solutions manual has a typo. Stupid solutions manual. So, yeah, if you're doing this one for homework, just be aware. Sometimes the person who prepared the written solutions has a typo, but that's not necessarily the case for the answer in mastering physics. So what am I doing wrong here? I don't think I'm doing anything wrong. I checked this number twice. This number is larger in magnitude than this number, so when you add them up, you should still get a positive number, and yet the book has a negative number. I'm not going to sweat it. Moving on. Let's do a very simple circular motion problem. This problem's not actually asking for centripetal acceleration, but I think we should tack that onto the problem. Number 28 tells us about the Earth is rotating. We're supposed to figure out the speed of a physics student. How about just any person in Miami, Florida, with a given latitude, and then Fairbanks, Alaska? So we'll have to draw a picture, do just a little bit of trigonometry before we can answer this question. But take note of these numbers here. 26 latitude, 36 latitude, and I will quote the radius of the Earth. Here's us looking slightly down on planet Earth so that we can see not only the sphere of the Earth, but the circular path traced out by somebody living up here, not at the equator, but at some higher latitude. So as the Earth rotates once a day, if you're curious, it doesn't actually take 24 hours to rotate once. It's 23 hours, 56 minutes, and some change. The reason for the difference has to do with the fact that we're going around the sun as we rotate. But we need to know the speed of somebody going around in a circle of arbitrary latitude. So the latitude is this angle right here. I'll call it phi. We measure latitude up from the equator. Now, this radius here, from the center of the Earth to any point on the sphere, it's not actually a sphere either. It's really an oblate spheroid, but we can pretend it's a sphere for now. That's what I'll call capital R, the radius of the Earth. But we actually want to know the radius of the circular path traced out by somebody at a given latitude. So I will use a lowercase r for that radius. This is the actual circle traced out by somebody at any latitude, phi. Now, if you live at the equator, little r becomes big R. And now let's take an actual side view where it's not like the camera's elevated a little bit. So from that perspective, we've got the radius from the center of the Earth out to where, let's say, out to the latitude where the person lives. And remember, that's measured from here. And then that circular path that they traced out, or trace out, would just have this radius. Here's the rest of the circle. Right, so that somebody living at latitude phi, they're going around and around. And you see that this radius is a little bit less than this radius. So this is big R from here to here. This is also big R. They're both radii of the sphere. This is little r. And do you see that if, let me close this triangle here, if this is phi, then alternate interior angles says that this is also phi. Okay, this is the person's latitude. That's the same as this angle right here. So take a look at this right triangle. The hypotenuse is big R, the radius of the Earth. If we multiply by the cosine of phi, that will give us the adjacent side, which is the radius that we want. So little r is big R cos phi. Let's see if that checks out. If you live way up here near the North Pole, you're making a circle of a very small radius. It's kind of fun to think about. If you lived at the North Pole and just stood still for a whole day, you're just turning around in circles. I don't know why that's amusing to me. What's your latitude up here? Well, this point is 90 degrees from the equator. We know that the cosine of 90 is 0, so that says you're moving in a circle of 0 radius, or approaching 0 radius, which is consistent with the picture here. And if your latitude is 0, if you're way down here at the equator, then you are moving in a circle of radius big R. The cosine of 0 is 1. 1 times R is R, big R I'm talking about. Okay, so that works. And they're really just asking for, they're asking for the speed. So the speed as you go around a circle, that would be your total distance over time. And we've already looked at this. That would be the circumference of the circle. Circumference of the circle divided by the time it takes to rotate once. Well, there's a special letter that we like to use for the time of rotation. That's the rotational period, capital T. Okay, 2 pi times big R cos phi over the period. And let's go ahead and calculate the period right now. That does not depend on the latitude. It doesn't matter where you are on planet Earth. It takes you about 24 hours to rotate once. So 24 hours, that's accurate enough, times there are 3,600 seconds in every hour. So let's figure out the period in SI units. I think I know this number, 86,000 something? Yeah. Every morning when you wake up, you've got 86,400 seconds to get stuff done until you got to do it all over again. And the radius of the Earth, for this problem, they give the radius to 2 sig figs, 6,400 kilometers. What is that, 4,000 miles? 4,000 miles to the center of the Earth. It's a very large rock that we're standing on. Okay. And for part A, we're told theta is, we're in Miami, 26 degrees. So here it is. The speed is, that's fairly close to the equator, 2 pi times 6,400 kilometers. So if I'm using kilometers, my speed will come out in kilometers per second, times the cosine of 26 degrees divided by that 86,400 seconds. And I'll do some rounding here, hence the approximate symbol. 2 times pi times 6,400 kilometers times the cosine of 26 divided by 86,400 seconds gives me a number that doesn't sound right. 0.4 kilometers per second. I must have done that wrong because I'm expecting, you know what, kilometers per second. That actually does make sense. Okay, once again, I guess I'll check this. You can just fast forward in the video. Yeah, 0.42 kilometers per second. Okay, so that's about 420. Yeah, insert obligatory 420 joke. 420 meters per second. That's almost 1,000 miles per hour, because remember, 1 meter per second is 2.25 miles per hour. So if I multiply by 2.25, yeah, 940 miles per hour. So, man, we're really moving fast just by virtue of being on a rotating rock. How come we don't feel it? How come you don't sense the fact that you're moving that quickly? Not to mention the fact that you're also hauling butt around the sun. Right? While we're rotating, which causes us to move really quickly, we're also making a giant orbit around the sun. How come we don't feel that? Well, remember, when you're on an airplane or a jet going 500 miles an hour, does it really feel that much different? As long as there's no turbulence and you're not turning, does it feel any different from being on the Metrolink at 80 miles an hour or even just sitting at rest? Your body doesn't have a speedometer. It's not equipped with a speedometer. We don't sense speeds. There's no, this is the idea that there's no absolute rest frame. You might think that you're at rest sitting here on Earth, but don't forget, you're on a rock going around the sun. So maybe you have to go to the sun to be at rest. Well, don't forget that the sun is making a giant circle around the center of the galaxy. You can imagine any point you'd like. That point is also moving around something else. So what the dealio? What is the actual place in the universe where you're not moving? It seems to be that there is no such place. Okay, why don't we, instead of doing part B where we would calculate the speed at Fairbanks, Alaska, that's just the same formula. It's not very interesting. Let's instead calculate the acceleration, because that may help us appreciate why we don't feel it. Okay, remember, we looked briefly at sports cars and what sort of accelerations they can produce. Some sports cars can accelerate at a rate of half a G or even a full G. Thrill rides maybe will accelerate you at 3 or 4 Gs. So those are easily detectable accelerations. You feel them. Let's look at how small the acceleration is due to your motion in a circle. So centripetal acceleration, I'll put A sub C for now. Later we'll call it A sub R. That's V squared over R. Well, let me go ahead and calculate the radius separately so I can plug that in. That's the 6,400 kilometers. And now I'm going to put it in meters. The radius in meters is 6,400 times 10 to the third times the cosine of 26. Okay, I get a long number. Let me put scientific notation. 5.75 times 10 to the times 10 to the sixth meters. Okay, that's the radius of your circular path when you live in Miami. Okay, 5.75 million meters. 5.75 million meters. And then my speed, I just calculated that in meters. That was the 420, right? 420 meters per second. Square all of that. And let's see what this is in SI units. 420 squared divided by 5.75 million. 0.03 meters per second per second. That is way less than 9.8. In fact, if I divide that by 9.8, I get 3 thousandths of a g. That's why you don't feel it. It's kind of a fun thought experiment. What if the Earth somehow sped up? If this cosmic hand came down and kept kicking the Earth around the equator until it got spinning faster and faster? Do you think you'd eventually feel the difference? If you go to an amusement park ride and get on one of those teacup style rides, you know, Disneyland's got that ride called the teacups, where you sit in these large cups, cup-shaped seats, and there's a steering wheel at the center, and you can get that thing spinning real fast and hopefully make your friends throw up in 6th grade. Not that that actually happened to me. Oops. So much for getting that girl to like me. But you definitely feel that acceleration. When you're being slung around in a circle, you feel the acceleration. Well, that's what we're doing all day, every day. We're moving in a big circle. How come we don't feel the acceleration? Despite this incredible speed at which we're moving all the time, that circle is enormous. We're moving in, think about it. If you're moving in a tight circle, like in your car, if you're a passenger in a car that's making a tight turn, you feel that. Well, the bigger you make that radius, the more your circular path begins to approximate just a straight line. So yes, we're moving in a big circle, but the radius is so large, we're practically moving in a straight line. We don't really feel the acceleration. But if you could go to a planet that was spinning much more rapidly, you just might feel it. And I'll go ahead and interject right here. Actually, what would happen if the Earth began to spin faster is that you would feel lighter. You would feel like you didn't weigh as much. And there's a crossover point at which you would become weightless. We'll talk about this after we've looked at the dynamics of circular motion in a later chapter, but if you spun the Earth fast enough, you would at some speed become weightless. Beyond that, you would need a force pulling you down to actually keep you on the Earth, and you would definitely feel that. Just like when you're on a roller coaster and you go over the top of one of the hills, you need that lap bar or the shoulder bars to keep you in. If the Earth spun fast enough, you would need a restraint like that to keep you from flying off into space, and of course you would feel that. Here's a 2D kinematics problem that isn't too challenging. Number 51, tennis player strikes the ball. The ball is 2 meters above the ground when she hits it, and the ball flies off the racket at 20 meters per second. That's over 40 miles an hour, slightly inclined above the horizontal. The net is 7 meters away, and the net is 1 meter high. We're supposed to figure out, does the ball make it over the net? So we'll look at my dingy little drawing here. I've grossly exaggerated the angle just to make it easier to visualize. This initial velocity vector has a magnitude of 20 meters per second, and we will need to know the components. Remember, this is v naught sine theta, v naught cos theta, so the net is 7 meters away. That's a 7. The ball leaves the racket 2 meters above the ground. Obviously, this is not to scale. This looks practically the same. The net is supposed to be only 1 meter high. So as with many of these two-dimensional kinematic problems, one of the axes will tell you how long the ball is in the air. And then the other axis will tell you how far it went in the other direction. That's just the way a lot of these problems work out. Usually if the ball strikes the ground, then it's the vertical axis that will tell you how long the ball was in the air or the time of flight. In this case, it's how long it takes to get to the net. So it's the x-axis that ought to tell us that. Let's apply the kinematic equation for position along the x-axis to first figure out how long it takes the ball to get there, because we do know the distance and we do know how quickly it's moving in the x direction. We can find that component of the velocity. Once we know how long it's in the air, we can plug that time into the kinematic equation for the y-coordinate and figure out where it is vertically when it gets to the net. If its y-coordinate is greater than 1, it's over the net. If the y-coordinate is less than 1, we know that it does not clear the net. So in the x direction, I'm using this equation. Delta x is v naught x times delta t. And if we want to be precise, we can label some times. How about t naught equals 0 seconds? We'll go with ball leaves or loses contact with the racket. It's a tough word to spell. T1, ball reaches the net. And by net, I mean, by reaches the net, I mean that its x-coordinate is equal to 7. So it may be above or below the net, but it has gotten to that x-coordinate. And then that means delta t Well, that would be T1 minus T0, which is just T1. Delta T is just T1 here because our initial time is 0 seconds. And if we choose an origin like this, why don't we just put the origin at the point directly below where the ball is launched from the racket? And that means the displacement would be x1 minus x0. Well, x0 is just 0. So the position at time 1, you see that? The coordinate for x at time 0 is 0 because the ball is at the origin. Well, it's directly above the origin at time 0. Okay, v naught, and how about I go ahead and substitute v naught x would be v naught cos theta. That's the x component of the initial velocity vector. Delta t we see is just t1. Well, we know this distance, or this coordinate. The coordinate of the net is 7 meters with respect to this origin. We know the speed that's given to us. We know the angle, so we can solve for t1. T1 would be the 7 meters divided by 20 meters per second times the cosine of 5 degrees. And you see how the units work out? Meters over meters per second gives us seconds up top. 7 meters divided by 20 divided by cosine of 5 is 0.351 seconds. Doesn't take long. Is there anything unrealistic about this problem? Well, we're pretending that there's no acceleration in the x direction. Notice how I'm missing the 1/2 at squared term? Is there really no x acceleration? I think as soon as that ball leaves the racket, it's already encountering significant air drag. Tennis balls definitely experience air drag during a game, and we've completely ignored that, which is not very realistic. So we're just getting practice with the special case of free fall. Gravity is the only force. Now that we know how long the tennis ball is in the air, let's figure out where the ball is vertically when it gets to the racket. So the position at time 1 equals the position at time 0. Notice I've put y naught over there. I could have had it over here, y1 minus y naught, that's what we call displacement, plus v naught y delta t, which is actually just t1 minus t0, but t0 is 0 seconds. And then I'll go ahead and acknowledge that the acceleration is negative g, so it's minus 1/2 g t1 squared. This g here, this negative g, is a sub y. I'm using final coordinate as initial coordinate plus initial velocity in that axis times time, plus 1/2 acceleration along that axis times time squared. My acceleration along the y-axis is negative g. Okay. Well, the initial y-coordinate, we start out 2 meters above the ground. And then v naught y, wouldn't that be v naught sine theta? So that's 20 times the sine of 5 degrees. I'm not writing units at the moment. And then we plug in the time that we've already calculated. Minus 1/2 g. Well, I think I've mentioned this. It's worth memorizing that 1/2 of 9.8 is 4.6. No, it's 4.9. Yeah. Minus 4.9 times 0.351 squared. We just plug stuff in. There's no unknowns in the right side of this equation. So if the y-coordinate comes out to be a number greater than 1, we know that when the ball gets there, it's higher. Whoops. If the y-coordinate here comes out to be greater than 1, we know that when the tennis ball gets to the net, it will be above the net. That means it cleared the net. See, none of you are here to yell at me when the notes are out of the camera frame. 20 times the sine of 5 times 0.351 minus 4.9 times 0.351 squared. All right, it's a little over 2 meters. So that cleared the net with no problem. Simple problem. You have to use one axis to figure out how long it's in the air. Then you can go to the other axis to figure out its coordinate along that axis. Number 14 from Chapter 4 is the same type of problem, but the roles of the two axes have been reversed, as you'll see. So this time we're told a rifle is aimed at a target. We're not told how high the rifle is above the ground, so that means we're not going to need that information. And the bullet strikes 2 centimeters below the bullseye, I suppose, or 2 centimeters below the point at which the rifle was aimed. Note that that displacement there is given in centimeters, so we will have to convert into SI units if we want to use 9.8, for instance. 9.8 is in meters per second per second. Part A, we have to find how long did it take the bullet to get to the target, and then what was the speed. Here's my scary gun. The target horizontally is 50 meters from the muzzle of the gun, and the gun was pointed straight ahead. This is actually where the bullet would go without gravity, right? Sans gravity. Newton's first law tells us if we're out in space away from gravity, that bullet is just going to keep going in a straight line at constant speed. But we are in a gravitational field here on Earth, and that causes deflection. This is the 2 centimeter drop from where the bullet would have gone. So ask yourself, which axis will help us determine the time of flight of the bullet? Does the bullet keep going until it hits the ground or until it hits some particular y-coordinate, or is it because it hits a wall? Well, you know what? That's not a great way to phrase the question. I guess it's not so much about whether it hits a wall or the ground. It's more about which information you have, which displacement you have. Like if you knew that the bullet struck the ground and you were given the height of the gun above the ground, that would be a vertical displacement. So you would want to go to the y equation to plug that in. But in this problem, we don't actually know the height of the gun above the ground. We do know how far the bullet has dropped vertically. That's a y displacement. So we would want to plug that into the y equation. Yeah. Hopefully that didn't confuse you. Let me just summarize. The information that we know is a vertical displacement. Let's use that in the equation for vertical displacement. You know, plug the information you know into an equation that contains that information. Before I can start plugging in numbers, I have to choose a coordinate system. I think for this problem, the best choice of origin would be at the muzzle, not here, because I don't actually know what the height of the gun is above the ground. So if I put the origin here, I have to make up some distance. There's no need to do that. Let's put the origin here. And just to shake things up, I'll put the x-axis forward, but I'll put the y-axis straight down, which means that the gravitational acceleration gets a plus sign this time, since it also points down, and I'm deciding to call that the positive direction. So the y-coordinate, I guess we can label some times here. T0 is when the gun is fired. T1 is when it hits the target, or just below the bullseye of the target. So the y-coordinate at time 1 would be the y-coordinate at time 0 plus initial velocity in the y direction times t1 minus t0. And let's, I'll put plus 1/2 a sub y delta t squared this time, just to show you all the steps. This is always a valid equation for constant acceleration between times 0 and 1. Now let's plug in what we know. The y-coordinate at the end is 2 centimeters from where we started. Well, this is the line for y equals 0. So the initial y-coordinate is 0. The final y-coordinate, it's not negative 2 centimeters, it's positive 2 centimeters because of my choice of coordinate system. I chose to put the y-axis positive downwards. You don't have to do that. So we're going to end at 2 centimeters, which is 2/100ths. 2/100ths of a meter is an initial y-coordinate of 0 plus, and then here's where you have to infer something. They didn't actually say that the initial y-coordinate that the initial y velocity is 0. They didn't tell you that. What they did tell you is that the velocity is horizontal at first. The gun is fired horizontally, which means that the initial y-coordinate is 0. Now, as the bullet falls, it picks up some downward velocity as well, but at t equals 0, the velocity is purely in the x direction. So that term goes away as well, 0 plus 0. And then because of my choice of coordinate system, my acceleration is actually positive 9.8, so plus 1/2 g times. And then just like before, let's just call the initial time 0 seconds, and this just becomes t1 squared. And you'll notice now that there's only one unknown in this equation. Really what I'm doing here is using this simpler version of the delta y equals v naught t 1/2 at squared equation. This often pops up when your initial or final velocity is 0. When your initial velocity is 0. This is often applicable. So I would not rely on this formula. It's best to always start from the more general equation, but sometimes it reduces to this h equals 1/2 gt squared. In this case, h is the height through which the bullet dropped vertically. T is how long it was in flight. Okay, we can solve this for T1. I'll just do this all at once. That would be 2 times 0.02 divided by 9.8, and then I'd have to take the square root. So we've got 0.04 divided by 9.8. Then I take the square root, and it only takes 6/100ths of a second. I'll round to the nearest thousandth. Okay, so we had to use the y equation to find out the time of flight. Why? Because they gave us the vertical displacement. That's what we already knew. We could plug that into the y equation and solve for the time. Now that we know that, we go to the x coordinate, and this part's more intuitive. If the gun, or if the bullet went 50 meters horizontally in this time, then all we have to do is say distance over time gives us the x velocity. So remember, delta x is v naught x delta t. There is no 1/2 at squared term because we're modeling the motion as having 0 acceleration in the x direction. So the initial x velocity would be the displacement of 50 meters in a time of 0.064 seconds. We're expecting a large number because we know that bullets move fast. 781. That is that's more than twice the speed of sound. Makes sense, right? A lot of bullets go about that fast. Next up is number 10 from chapter 4. Uh-oh, what's this CALC? Does that mean we're going to have to do some calculus? Well, they give us the velocity as a function of time, and you'll notice that the x-coordinate is proportional to time. That sounds familiar because for constant acceleration kinematics, we have that equation that says delta v basically is acceleration times time. V equals v naught plus at. That's kind of what this looks like, except for the fact that the y-coordinate, or the y-component of velocity, has a t squared. And I don't remember any constant acceleration kinematic equation for velocity that has a t squared. Yes, there's the 1/2 at squared, but that's for the displacement, not for the velocity. So I suspect, aka I know, that this is actually non-constant acceleration. One way to see that immediately is to take the derivative. Remember, acceleration is the time derivative of velocity. When you take the derivative of the y component, you get 4t, which is not a constant. That depends on time. So we're going to have to go back and redevelop our kinematic equations for non-constant acceleration. How do we accomplish that? Well, it's a very straightforward generalization. It's not even really a generalization. It's just an application of concepts we've already done in one dimension. I hope you recall that the displacement between two times for one-dimensional motion is the area under the velocity curve versus time. If I take this x initial and put it on the other side, x final minus x initial, that's what we call displacement. This equation says that displacement is the area under the v versus t curve, something you should have memorized from earlier chapters. We can make the same statement about the y-coordinate. The change in y-coordinate, or displacement along the y-axis, should be the area under the velocity versus time curve, but I really should have specified previously the change in x is the area under the v sub x versus time curve. In other words, you have to integrate the x component of velocity to get the change in x position. To get the change in y position, or y-coordinate, you would take the integral of the y component of velocity. So you've seen these equations before. The only thing we've added here is the subscript to specify which axis we're talking about. Is there a way of stating these two equations simultaneously? Can we write them more compactly? Taking a cue from what we did just a moment ago, let's put some parentheses around corresponding quantities And now this column vector has components equal to the final position, so I could call that final position vector. The components of this column vector are the initial components of position vector, and then these are the components of the vector velocity at any time. So perhaps we can say that the final position vector is the initial position vector plus the integral in time of the velocity vector. And that probably looks a little foreign to you. What does it mean to integrate a velocity? I'm guessing you have not yet talked about that in your math classes as you're taking intro mechanics here. To add a vector, I mean, we know in one-dimensional calculus to take the integral of some function f of x with respect to x, what you're doing is taking the area under that curve, or you can think about it as adding up the areas of all those little skinny rectangles. This is something altogether different because it's a vector. Here's one way you can think about it. Don't forget that an integral is really like a sum. In fact, the integral symbol looks like a giant S for sum. So you're adding up a bunch of vectors. Now, each of these vectors, the velocity at any time, that's a finite vector it's got a finite length. But what do you get when you take a vector of finite length, like velocity, and multiply it by dt? Doesn't that shrink it back down to something infinitesimal? So v dt at any time is an infinitesimal vector, and you're going to add up a whole bunch of those infinitesimal vectors between t initial and t final. What do you think you get if you add up an infinite number of infinitesimal vectors? You can imagine you might actually get a finite vector, which is what we better get, right? Because this is really delta r. This whole thing is delta r. Remember that? Final position is equal to initial plus delta r, and delta r is a finite vector. In any case, you don't really have to be thinking about it when it comes time to integrate. All you do is integrate component-wise. That's it. So if you're wondering how to actually procedurally carry out the integration, you just integrate v sub x between the two times. You integrate v sub y between the two times, and then the two numbers that come out of those integrations, those are the components that come out of this vector integral. Simple as that. And that'll be clearer after we do an example. We can make a similar statement about the relation between not position and velocity, but the relation between velocity and acceleration. So remember, in one-dimensional motion, change in velocity, just put this on the other side, change in velocity is the area under the acceleration curve. That's true in the x-axis, and it's true along the y-axis. So as before, let's put some column vector parentheses around corresponding quantities. And a compact way to write both of these equations simultaneously would be to say that the final velocity vector is the initial velocity vector plus the integral of the acceleration vector between those two times. So what comes out when you integrate a vector? Another vector. This whole thing is a vector. And what would that vector have to be? Well, v final equals v initial plus delta v. This whole thing must be delta v. When it comes time to actually carry out the integral, again, you just integrate component-wise. What could be simpler? Let's put those two results together. And this is how you would proceed with non-constant acceleration problems where you're looking at motion in a plane. You would have to integrate the acceleration vector to get the change in velocity vector. You would then have to integrate the velocity vector to get the change in position. Same prescription from the one-dimensional case, but now it's a vector. Let's do a problem where we have to use this. In fact, we already started this problem. This is number 10. So take note of the velocity as a function of time. This is not the velocity at any particular time. It's not initial velocity. This is the velocity at all times. And they do give us, at t equals 0, they give us the position. In other words, that's r naught, the position at t equals 0 seconds. And I'll remind you once again, r sub 0, the sub 0 is just a label. It doesn't have to be the position at 0 seconds. Really, it's the position at t0. But usually we choose t0 to be 0 seconds because that's the most convenient choice. So I'm going to write down the initial position vector. And then from that, I will figure out the car's position at some later time t. They're asking for the position at time t. We know we're going to have to integrate. They're also asking in part b for the acceleration vector, but that's easy. We've already talked about how acceleration is merely the derivative of velocity. Here we are. Initial position vector. I've chosen to write it in that column notation. So this is the x component, this is the y component. You don't have to do it this way. Your solutions manual likes to leave everything in terms of basis vectors. So they'll say, for instance, 3 in the I hat plus 2 in the j hat. That's perfectly fine. I just think this is easier. You want to do the easy one first? Let's do the acceleration. That's actually part B. I'll do that first. So the acceleration at time 2 seconds. Well, that would be the time derivative of the velocity vector. And I'll go ahead and use this notation where you say evaluated at t equals 2 seconds. dv dt is, well, I suppose I could say, well, that's the time derivative of this vector. And now we just differentiate component-wise. Remember that video from a couple weeks back where I showed that as long as your vector is expressed in terms of the Cartesian basis vector, so this is the component along I hat, component along j hat. If that's the case, then the derivative of the vector can be found just by differentiating the components, which is the first thing you would guess. And now this is easy. The derivative of the x component is -3. Here we have to bring down the 2, 4 times t to the first power. Okay, so these are the components of my velocity vector at any time. And that means that the acceleration at time 2 seconds, specifically, would be, well, -3 is a constant, 4 times 2 is 8. And there it is. We might as well plop in our units. That part was easy. Now, am I missing anything? They just want the acceleration vector. They don't say find the magnitude, which we could do with Pythagorean theorem. They don't say find the direction, so we're done there. For part A, how do we find the position at time 2, knowing the position at time 1 and the velocity at any time? Well, we just looked at this in PowerPoint. Here my final and initial times are 2 seconds and 0 seconds respectively. So symbolically I would say the position at time 2 is the position at time 0, which we were calling r naught, or r sub 0, plus the integral of the velocity vector between those 2 times, just like in the one-dimensional case. Final position is initial position plus the integral of velocity between those 2 times. I can't really say it's the area under the velocity curve, because that's only true in the one-dimensional case. Now we're talking about velocity vector. So we don't have that nice graphical interpretation anymore now that we've moved on to 2 dimensions. Okay, so R2, or the position at 2 seconds, that would be my initial position of 3, 2, plus, and then here's a notation I think is fine to use. I'll put a giant integral sign. I'm integrating from times 0 to 2. I'm integrating this column vector where I will plop in the components -3t and 2t squared. So this is not some kind of standard notation. I don't think I've seen it in our book, but I think it's fairly clear. This is a vector which we could write as a column. We take the initial position vector in column form, and we're integrating this vector. This is that velocity vector. I've just written it as a column, and of course to integrate it we just integrate the components separately. All right, that's 3, 2 plus, and I think we can do this in our heads. Remember, if you're integrating a polynomial, then when you plug in the limits, if the lower limit is 0, any polynomial with powers equal to 1 or greater will just give you 0 when you plug in 0, right? Like here we're going to come up with t squared over 2, or 3/2 t squared. When you plug in a 0, you just get 0. So I really only have to integrate this and then evaluate at the upper limit. If this was a function like sine or cosine, that would not be the case. I would have to plug in both limits. Okay, the antiderivative here, -3/2 t squared. Yeah, you know what? I think the way I was speaking a moment ago, I said I was going to actually plug in 2, and now I'm just leaving it as a variable t. Let me do it that way. So I will evaluate the position at any time after 0 seconds, find the function that gives the position at any time, and then I'll evaluate that at 2 seconds. What's the antiderivative here? 2/3 t cubed. Okay, so if you'd like to know the position at any time, you take the vector 3, 2, and you add this vector after plugging in the particular time. I'll just fold this paper over here, and we can evaluate this at 2 seconds. So the position vector at 2 seconds is 3, 2 plus, okay, what do we get here? Well, 2 squared is 4. 4 over 2 is 2. 2 times 3 is 6, so it looks like a -6. And here, 2 cubed is 8. 8 times 2 is 16, and then 16/3. Darn it. I don't think we can simplify that anymore. Okay, so now we can add these two vectors, and I get -3. If I'd like a common denominator, I don't even care. Let's do a decimal. What's 16/3 plus 2? Did I do that right? 16 divided by 3 plus 2. Yeah, 7.33. And I guess I'll be lame and check the solutions manual to make sure that my answer is the same as theirs. -3 and 7.3. Cool. All right, I prefer my notation. You can do it however you like. If you prefer to use the notation that the book sticks with, I will understand that. That'll look just fine if something like this showed up on an exam problem. Let's knock out one more two-dimensional kinematics problem for this video. I know we haven't looked yet at angular velocity, which is a quantity that we represent with the Greek letter omega. So I haven't talked too much about that, and I have not talked about tangential acceleration or non-uniform circular motion. So that will come. I'm trying to avoid using language specific to this class in this semester so that these videos will be applicable in the future. So I'm not going to talk about your exam and the content on it. Okay, we'll save non-uniform circular motion for another presentation. This is the one about the sand moving down the conveyor belt in some factory, and it slips off the end of the belt, and it's been designed just so that the sand falls into this pipe where it's taken off somewhere else. So we're given the dimensions here. Notice it's where the sand actually leaves the conveyor belt and enters free fall. That's the point that's 3 meters above the lip of the tube here. So don't be confused about the spatial extent of this conveyor belt. The top of the belt is also inclined at 15 degrees, just like the bottom. But this is really the point right here where it enters free fall motion. Prior to that, it's still being supported by the conveyor belt, so it's not in free fall. And we're supposed to figure out what this necessary distance is. Notice how they've got the end of the arrow in the middle of the tube. They didn't tell us how wide the tube is, so the problem's not that complicated. We're not supposed to take into account the diameter of the tube and how much the sand might spread out. We just pretend it's a narrow beam of sand and it's entering at the center of the tube, so who cares what the diameter of the tube is. So let's go back to my lousy drawing. And I've just represented the conveyor belt with a single line segment here. Right here is where the sand leaps off the top belt and it enters free fall. It follows this parabolic trajectory here. And let me drop a perpendicular down. We're interested in this distance, D. How far out does the pipe need to be? Because obviously if it's placed this too far to the right or left, the sand will miss. So remember how I said, look at the information you're given, and that will guide you in choosing which equation to plug some quantity into? Well, maybe before we answer that, let's put the last piece of information on here. The initial velocity vector of the sand is always tangent to its trajectory. So that velocity is that 15 degrees below the horizontal. Remember, the sand was already moving in this direction. So it's going to continue that velocity in the moment just after lifting off of the conveyor belt. Then the velocity will start to change because of the gravitational acceleration. But this is also 15 degrees, and I can visualize the components here. There's going to be an x component of the initial velocity and a y component. And the initial speed is given in the problem. It's 6 meters. So I'll say v naught equals 6 meters per second. Okay. which piece of information will allow us to choose, think of it this way, which axis will tell you how long the sand is in free fall before it enters the pipe? Well, we know that it has to fall a distance of 3 meters vertically. And because we were given the launch angle and the speed initially, we can find the initial y component of the velocity vector. So since we know how fast it's already moving vertically when it lifts off the conveyor belt, and we know the distance through which it will fall vertically, we should be able to figure out how long it's going to take to get to the pipe. Once we know that number, the amount of time it takes to hit the pipe, we can figure out how far it will travel during that time, because we also know the x component of velocity. Then we just use distance equals velocity times time. The more practice you get with these problems, the better you will get at knowing how to start. Practice is really your best defense. Is that the expression? Best defense against what? I don't know, test anxiety, perhaps? Okay, so we'll start with the y equation. Good old delta y equals v naught delta t plus 1/2 y acceleration delta t squared. That's our kinematic equation. As usual, we could say, well, t naught equals 0 seconds. That's when we begin free fall, or the sand begins free fall. And then t1 is the natural choice for when the sand enters the pipe. Okay, so t naught happens here, t1 happens here. And that means that displacement would be y1 minus y naught equals v naught y. And I'm going to go ahead and insert now. This is v naught sine theta times the time interval. The time interval being t1 minus t0, but remember t0 is 0 seconds, so that's just t1. And before I decide whether to write plus g or minus g, I have to choose my coordinate system. I'm just going to go with the usual plus y in this direction and plus x in that direction. That means that my acceleration in the y direction would be negative g, so minus 1/2 g t1 squared. Okay, and I just realized this is a subtlety. Remember my spiel about how you can only use this formula for the resolution of a vector. In this case, we're talking about the velocity vector. You can only use those formulas, v naught sine theta and v naught cos theta, if you follow the conventions. The angle has to be measured from the positive x-axis, and you have to take into consideration whether your angle is swept out counterclockwise or clockwise. So this velocity vector is actually below the horizontal, which means this angle needs to be evaluated as a negative 15 degrees. That's the only way to get a negative number to come out of this formula. We know the velocity in the y direction has to be negative initially, because we can see that from the picture. Now, as far as the displacement, well, if we start at 0, this is y equals 0, and that means we would end at y equals negative 3. So negative 3 minus 0, that's a displacement of just negative 3. You can also just reason, well, the displacement has an absolute value of 3, and it's in the negative direction. Hence, the displacement is negative 3. Okay, so then we've got 6 meters per second times the sine of, be careful, negative 15 times t1 minus 1/2 g t1 squared. Okay, and it looks like, darn it, we're going to have to use that blasted quadratic formula. Yep, I'm looking at their solution, and there's no way around it. This is a quadratic equation in t. Good, it's good that we're doing one of these. I'd also like to point out, if you didn't want to mess with, thinking about the actual sign, SIGN, of the angle, you could just recognize, okay, I've got a triangle, I want the opposite side, so I would use the sine function, and since it points down, I have to insert a minus sign. So you could have done sine of 15, not negative 15, and then you add the minus sign out front. Either way works. Okay, I'm going to put this in standard form. Remember, 1/2 of g, that's 9.8. I'm sorry, that's 1/2 of 9.8, which is 4.9. So I've got a 4.9 t1 squared. I put that on the other side now. And then plus, because this would come out negative, and then I put it on the other side, it gets a plus sign now. 6 times. So that's 1.553 t1 minus 3 equals 0. I could divide everything by 4.9 first so that my coefficient of the quadratic term is 1. That would make it easier if I was going to implement the quadratic formula manually, as in on paper and use a calculator. But I'm just going to cheat and use, oh, you know what? It's been a while. I'll do it with the scientific calculator. How's that? So that means maybe it would be best to divide the whole thing first by 4.9. t1 squared plus, what's 1.553 divided by 4.9? Okay, 0.3169 t1 minus 3 divided by 4.9, 0.6122. That's got to equal 0. All right? Now, there are 2 roots to this equation. Remember, complex roots always come in pairs. So either they're both complex or they're both real. Now, when you look at the picture here, with the dimensions given, it seems reasonable. Yeah, we're going to get a real number. Obviously, there's some real number that describes the time at which the sand enters the pipe. So I expect to get 2 real roots. How are we supposed to know which one to keep? Well, one of them has to be obviously not it. And that makes me think that one of the roots will come out negative, some negative time. And maybe I'll give you some interpretation of what that negative sign would mean. So t1 would have to be, remember, it's negative b plus or minus the square root of b squared minus 4ac all over 2a. By the way, we're all familiar with the quadratic formula. What about if it was a cubic formula or a cubic equation? Is there some magic formula that will always give you the roots? For a long time now, I've been vaguely aware that there is. I had just never seen it. But there's an awesome video on YouTube. I think the guy's name is Mathologist or Mathology. And he's got like an hour-long presentation where he shows you the formula for a cubic equation and how to use it. And he throws in some history. I'm sure you don't have time to watch that right now. But okay, so negative b would be negative 0.3169 plus or minus square root of b squared, 0.3169 squared, minus 4ac. Well, a is 1, so 4 times 1 times negative 0.6122. All of that over 2 times a is 1. All right. If it sounds like I'm regurgitating a bunch of gobbledygook right now, it means you don't have your quadratic formula memorized. I'm sorry, you can't read this. This is 0.3169 squared. So I'll do the radicand first. 0.3169 squared. And that's supposed to have a minus sign. Minus 4ac. That's a negative 0.6122. That would have messed me up. 0.3169 squared plus 4 times 0.6122. I say plus because the 2 minus signs cancel. Did I hit equals? Yeah. Now I take the square root. So it's negative 0.3169 plus or minus 1.5966 all over 2. Now, very clearly, the root with the minus sign is a negative number. We don't expect a negative number. If this is 0 seconds when the sand leaves the belt, then obviously it's going to enter the pipe at some positive time. So I'll go ahead and use the plus sign. Then I'll divide by 2, and this should happen at a time of, I'll put ... t1 equals 0.639 seconds. Really, it rounds to 0.64. I'll go with 0.64 in the next part of the calculation. Now, if you're wondering what the math is telling you with that second root, that negative root, check it out. As far as we're concerned, the motion begins here, the free fall motion. That's when it goes into this parabolic trajectory. But what if prior to t0 it had not been on a conveyor belt? Just rewind, so to speak, continue this parabola backwards in time. If you think back to the equation we wrote, we're really just looking for when the y-coordinate is negative 3. We found that in the future, it happens at 0.639 seconds. At this time, the y-coordinate is negative 3. But if you go back in time prior to t0 and follow that parabola back, there was another time at which it was at a coordinate of -3, a y-coordinate. That would have been the significance of that other root. So oftentimes there is some physical meaning you can assign to that. Can I fold this down? Yeah. Okay, now that we've got the time, how do we figure out what this distance needs to be? Well, that's a lateral displacement. We can go with x displacement is initial velocity in the x direction times delta t plus, well, there's no 1/2 at squared term because our axes are vertical and horizontal. Gravity has no component horizontally, and we have ignored air drag. And our sand particles do not have rocket packs on them, or jet packs. So there's no other source of acceleration. All right, so the displacement, look at it. Here's the origin. The displacement is d units to the right. That is the displacement. That's what we're looking for, as a matter of fact. Now the x velocity, that would be v naught cos theta. We want this component. And I can just go ahead and use v naught cos 15. That'll give me a positive number. So v naught cos theta, or 15, times, and delta t is t1 minus t0, but t0 is 0 seconds, so it's really just t1. And now I can plug in numbers. That's the 6 meters per second. That's how fast it's moving, but we need the component that's horizontal, and then multiply by how long it's moving at that velocity in the x direction, and we've just solved for that. So we had to use the y-axis to figure out the time of flight, if you'd like to call it that. Meters per second times seconds will give us the distance that we want. 0.64 seconds times the cosine of 15 times 6 meters per second. 3.71 is the answer that I get. That's how far the center of that pipe needs to be from the point at which the sand leaves the belt. Does that check out? The solutions manual has 3.7. Yay!